All right, guys, today we're beginning our unit on chemical reactions, right? We're seeing how matter changes, and then we're going to be doing, I don't know, good thing, bad thing. There's going to be some good many calculations in this unit. So, guys, let's get started. Extremely important lesson. Don't want to miss it. Stay tuned. She says, "For Pete's sake, Robert, it's time you saw a mechanic about these emissions of yours." Car emissions. Mold. So you guys, this is the big topic for today. This is really important. We're going to be talking about a mole for the rest of the semester. What is a mole? Mole, you're thinking, what is a mole? Are we talking about that mole, like the mole on Marilyn Monroe? Are we talking about, no, not that mole, silly. Are we talking about that kind of mole? You guys know a mole, right? It kind of lives in the ground. Isn't that the cutest little thing you ever seen? We're not talking, if we're in a biology class, maybe that's the mole we're talking about. We're not talking about that mole. Not that kind. Mole we're talking about in chemistry, we call it a chemist's dozen. Okay, you just think about, you guys, right? You think about, it's a chemist's dozen. You guys know what a baker's dozen is? You ever heard of baker's dozen? You know, a baker's dozen, it's not 12, a dozen's 12, but baker's dozen is 13. The idea is that the baker, right, makes 12 donuts or 12 cookies, and then they kind of keep them for themselves, right? So it's a baker's dozen. But you think about it, a lot of the things that are sold by a certain amount, like roses sold by the dozen, donuts sold by the dozen. You could buy a 6-pack of soda. Do they even sell 6-packs of soda anymore? I don't know. But you guys think about why do we do that? Why do we sell eggs by the dozen, for example? You guys, wouldn't you guys agree it's just a lot more convenient rather than selling it by the individual? They just figured, yeah, when people buy eggs, in general, they probably want to buy a dozen. Same with donuts. And think about paper. You guys know how paper's sold? You guys know the computer paper that we get tons of it here at the school. Not so much now with distance learning. You guys know how paper's sold? It's sold by the ream. You guys know how much is in a ream? It's actually 500. So why did they do that? They just figured that's a good, convenient number to use when it comes to individual paper. So chemists have a number that a chemist use, which is going to be very convenient to the chemist. That's what a mole is. Okay, so it's a certain value. And what it does is it bridges the gap between the theoretical and the practical. You're like, what? Well, let's talk about this. So theoretical. Okay, so theoretically, so let's start with a hydrogen atom. That's our most basic atom. What's the theoretical weight of a hydrogen atom? What I'd like you guys to do is look on your periodic table. And if you guys look on the periodic table, you see what's the weight of a hydrogen atom. It's 1. It's 1 AMU. You remember what AMU is? Atomic mass unit. Now, the reason why I put that theoretical, because it's not like you could take one hydrogen atom and put it on a scale. There's an electronic scale. I can't put it on a scale and then get a measurable mass. It's too small. We'd say it's theoretical, okay? But let's say I get a pile. Let's say I get a whole pile of hydrogen atoms. Now, obviously, this is really theoretical because hydrogen's a gas. It's not like you're going to be able to confine a pile. But let's say we're able to confine enough such that I can get a practical weight. Now, you can think about it, you guys. What would be a unit that you could use practically? Hopefully, you guys are realizing a lot of the scales we're going to use, we use the metric system. It's not going to be pounds or ounces. It's going to be grams. So let's say I get enough hydrogen atoms so I can get a gram pile, right? So I could have a gram of hydrogen in a container. I could put it on the electronic scale and measure out a gram. That's a practical weight, okay? So now let's do the same with oxygen. So what's the theoretical weight of oxygen? You guys would look on your periodic table. You guys look at the bottom number on oxygen. You guys are going to see it's 16 AMU. You guys, at this point, I'm just rounding to the nearest whole number, but you guys know it's not always the whole number. Anyways, let's say however many atoms I got of hydrogen in this pile, let's say I get the same amount. You guys know when I do the quotations, that means the same as the one above it. So if I get just as many oxygen atoms here as I had hydrogen atoms here, the question is how much would that pile of oxygen atoms weigh if I put that on the scale? You guys think about it. How much would that pile of oxygen atoms weigh? Wouldn't it weigh 16 grams? And why is that? Because each oxygen atom is 16 times heavier than a hydrogen atom. If I have just as many oxygen atoms as I have hydrogen atoms, wouldn't my pile be 16 times heavier? So you guys get it? And so the same with nitrogen. What's the theoretical weight of nitrogen? I look on the periodic table, it's 14 AMU. That's how much an individual nitrogen atom weighs. Let's say I get just as many nitrogen atoms as the ones before. How much would that pile of nitrogen atoms weigh? When you guys agree? Shouldn't it be 14 grams? 14 times, just like each atom is 14 times heavier than hydrogen. Therefore, the pile should be 14 times heavier. And then lastly, we just do carbon. I think you guys get the idea. Is 12 AMU. What would that pile weigh? It would weigh 12 grams. Okay. So you guys, at this point, you guys see this is pretty nice. Look, the practical weight is the same as the AMU weight. It's just you just change the units. So at this point, I was hoping that this would elicit a question. Like, we still haven't answered a question, which is really a key burning question. At this point, if you guys were to look at this, what would be a question you'd have? You say, okay, I kind of get that, Mr. Wilson. So then, what's the question? I would hope it would be, well, how much is in a pile? Right? Because you guys, when you guys agree, this number here is a significant number because that number allows us to go from the theoretical to the practical by just changing the units. And when you guys agree, there's a certain number of atoms in this pile. So that pile, what's that pile? That pile is a mole. You guys remember, a mole is a chemist doesn't. It's the number that chemists use to make life easier for the chemist. And you can see why. So it says the number of atoms or molecules needed such that the practical gram weight is equivalent to the theoretical AMU weights, just like we saw on the previous slide. That is a certain number that allows that to occur. What you just have to do is change the tags or the units. The units are like from AMU to grams. So now what's a mole? So that still leads to the question, what's the question? Well, how much is that, right? We understand the significance of whatever that number is. We call it a chemist dozen. Here's the number, guys. And you think about it, what kind of number would you guys predict? When you would predict an extremely large number, you guys, this is an extremely, extremely large number. I don't know if you guys remember at the beginning of the semester, I wrote a number across the board, 602 followed by 21 zeros. And I said, hey, and we were learning like scientific notation. I said that number isn't just an arbitrary number that I made up. It has some significance. Well, now 3 months later, we're coming back to that. 4 months later, we're coming back to that number. This is the number right here, extremely, extremely large. And why would we expect extremely, extremely large number? Because aren't chemists dealing with atoms, which are extremely small, and even in the smallest sample size of a particular matter, you're having trillions and trillions of atoms. So it's not surprising that the number that's convenient for chemists is going to be an extremely large number. So that's the number, right? If you write it out, you just have to move the decimal 23 places. But obviously, this is a lot easier to write than this, and that's why we use that. So that's a mole. You guys get this? Just to try to communicate the magnitude of a mole, right? Check this out. You guys don't have to write this down. Don't write this down. If you were to count every grain of sand on all the beaches in the world, some people are like, how the heck are you going to do that? You wouldn't actually have to count every, because you can actually kind of estimate it. What you would do is just take a sample of sand on a beach, like let's say Imperial Beach, and let's say you take, a square foot sample. Now that would be really tough, and you count every grain of sand. That would take you a long time to do it. But then just take that number and then multiply it by the square miles of all the beaches, and you could probably look that up geographically. If you did that and you count it and you put it all together, we're talking tremendous. Every grain of sand, that would be less than a mole. This number right here is greater than all of the grains of sand on all the beaches in the world. It's a true statement. It seems kind of ridiculous to say it, but it's true. It says couch, Doritos, dumb judge shows, nap. It says can't start the day without my morning briefing. You know how like presidents get a morning briefing, like CIA and gives a briefing on all the terrorist threats and things and economic situations all around the world. Those are his briefings. Hopefully you guys will have a little bit more noble daily briefings than this guy did right here. So anyways, atomic mass. You guys remember that's the mass of an atom, right? Atomic mass. Remember I allow you to round off. Probably, ideally you guys would round to the 10th place, not just the whole number when you guys look on the periodic table. But it's more specifically, I think we're going to use this term more frequently, called the molar mass. And that would be, what's the molar mass? That's the weight or mass of a mole of atoms. So if you had a mole of atoms, remember that's the chemist does, and it's that amount. And how much is a mole now? Now we know 6.02 times 10 to the 23rd. Okay? So, example, let's say we do oxygen. So what's the mass of oxygen? 16. Where did I get that? I'm just looking on the periodic table. I look at, look at oxygen, and I see what its mass is, 16. And it's 16 what? Well, theoretically, it's 16 AMU per atom. That means each atom weighs 16 AMUs. But what is probably a better term? I'm hoping you guys would put a little pause here and think. I could say 16 AMU per atom, or I could say what? 16 what? Can someone, as if you guys are going to respond back to me, change the units here. Rather than saying 16 AMU per atom, because remember, that's theoretical. We don't deal with individual atoms. It's probably better to say 16, two-part unit, 16 grams per mole, right? Because wouldn't one mole, 6.02 times 10 to the 23rd atoms of that, weigh 16 grams? Remember we were talking about it bridges from the theoretical to the practical. All you do is just change the units. And this is practical. So you guys notice we say grams per mole. Now you guys, an abbreviation for grams is G. Now, an abbreviation for mole is MOL. You're like, thanks, you're just saving me the E. Why can't it be M? Because you guys remember M is already used for meter, so we can't use M. So MOL is actually the abbreviation for mole. So rather than right now mole, MOLE, just put MOL. Okay, let's do oxygen. Because you guys know oxygen actually comes as a diatomic molecule, so it's probably more appropriate to do O2 rather than the single atom. So what's the mass of the molecular weight, right? Because it's a molecule. What's the molecular weight? Isn't it 32? You guys see what I did? Well, if it's O2, and I look on here, I'm just pointing here, I know you guys can't see it, but I'm looking, I see 16. Well, there's 2 oxygen atoms, each weigh 16, so isn't the total, I just add those together, isn't it 32? So it's 32 AMU per molecule, or what's the better way to say it? In fact, I don't ever want you guys saying this because we don't really talk about the theoretical. What would be the practical thing I would say for the molar mass of O2? 32, you guessed it, grams per mole. That means if I had 1 mole of oxygen molecule, 6.02 times 10 to the 23rd, how much is it going to weigh? 32 grams. Okay. And you guys are going to start seeing the practicality of this when we start doing calculations. You kind of have to understand it. And it's just going to make, it's going to allow us to count for the atoms in the reactions that we're looking at. Think about CO2. Okay. What is the molecular weight of CO2? So what would you do? See, I could switch to a periodic table, but I think that would take too long. I would just show you, I'm looking at carbon, right? It's got carbon, so I'm finding carbons right here. I look at the bottom, it's 12, okay? And then oxygen, I look at oxygen, it's 16, but there's 2 oxygens. So I go 16 plus 16 is 32, plus the 12 from carbon, that's 44. And what can we say again? We can say 44 AMU per molecule. So each molecule would weigh 44 atomic mass units, or a more convenient, more appropriate thing to say would be it's 44 grams per mole. That means 1 mole, if I had 1 mole of carbon dioxide molecules, it would weigh 44 grams. Okay, you guys, we're going to do a little review, okay, just to see if you guys can pick this up. Let's do this. Okay. So you guys, let's say you're a lab tech and the professor tells you you need to prepare 0.5 moles of NaCl. Let's say that's how much is necessary for a demonstration or a lab. So what are you going to do first? You're going to go to the stockroom. You're going to get your salt. Okay, got my salt. I need, how much of this salt do I need? I need 0.5 moles. You're like, would you guys know how much 0.5 moles is? No, you wouldn't. That's a certain number, but it's not like you're going to be able to tell that. But what could I do? What can I measure about this? I can't measure the individual sodium chloride units, but what could I measure? Guys, couldn't I measure the mass? So what would I want to do here? If I want to know how much of this I need, wouldn't I want to know what's the equivalent mass of this for 0.5 moles? So this is a pretty practical thing that a lab tech would have to do, some of the calculations, right? So I want to go from moles, so you guys, we're going to do a little unit analysis. I want to go from 0.5 moles of NaCl to grams of NaCl. Because if I know this, and you guys agree, if I know this, then I can just weigh it out right here. So I set it up, you guys remember unit analysis, I get my endpoint, here's my start point, and now you've got to figure out, how do I go from moles to grams? You guys remember from the previous slide, the link, the bridge between moles and grams is what's called the molar mass. So what do? I look up the molar mass of sodium chloride. So where are you going to do that? You guys are going to look on the periodic table. So now we'll go to a periodic table. So I don't know if you guys can see here at this point. Hopefully you guys can see. Sodium, it says 22.99. You guys, if you round to the 10th place, it would be actually 23.0. So that's 23.0. Look at chlorine here. Chlorine is 35.45. I don't know if you guys can see it, but it's 35.45. Now, you guys, if we just round to 35, that would be way too much rounding. You're going to get a number that's pretty off. So what I want you guys to do is get in the habit of rounding to at least the 10th place. So if it's 35.45, if I'm rounding to the 10th place, that would be 35.5. So sodium was 23, and chlorine was 35.5. So if I add those together, it's 58.5. And you guys remember, if that's the molar mass, what does that mean? That means grams per mole. 58.5 grams per mole. You guys see, that's and you guys, this is what bridges the gap between moles and grams, because look, what does this mean? It means 58.5 grams of salt is equivalent to 1 mole of salt. That's what that means. And you guys look, I got my 2 units, mole to gram. So what do? I only need one. You guys remember our unit analysis? This is only one road on the journey. So I do one set of parentheses. Mole is on top. So which one of those do I want to put on the bottom to cancel out? I'm going to put the 1 mole. 1 mole of sodium chloride is equivalent to 58.5 grams. You guys look, so look, moles cancel out. Notice I don't cancel out any numbers. Moles cancel out, and what's the only unit I have left? Grams, which is what I want. Both the numbers are on top, so what am I going to do with them? I'm going to divide. And so what you're going to get is, it's about 29. I'm just kind of rounding a little bit. It's about 29 grams of sodium chloride. So now, you guys see, now I have a number I can use. How much is 0.5 moles of sodium chloride? Oh, it's 29 grams. So now, if I'm a lab tech and I need 0.5 moles of this, how am I going to get 0.5 moles of it? I'm going to get 29 grams. So how do I do it? You guys, just a little, because when we return, because I'm very hopeful that we're going to return to class, you guys are going to have to use electronic scales. You turn it on, and you're not going to pour the matter right onto the scale itself. You're going to use a weigh tray. So what do I need to do? I put the weigh tray on there, but I don't want the weight of the weigh tray. These are pretty sophisticated. They have a 0 button, so I can push the 0 button, and it already subtracts out the weight of the weigh tray. And then what do I proceed to do? Add 29 grams of salt. And then I would have that prepared for the lab. Okay, guys, let's do another one. Okay, let's say, I blow up a balloon. You guys, among other things, what do you think is primarily in this balloon? I know you're like thinking, oh, Mr. Willison's hot, funky breath. I get it, okay. But primarily, what was I breathing out? Carbon dioxide. This would be primarily carbon dioxide. So let's say, if I want to get the weight of this, if I wanted to see how much carbon dioxide do I have in this balloon? How much carbon dioxide do I have in this balloon? How would I figure out how much carbon dioxide I have in the balloon? Some people are thinking like, well, one thing we can do, what could I do with this? Couldn't I weigh it? Now you guys, if I wanted to weigh the carbon dioxide, would I just put the balloon on there, like there? You guys see what the problem with that would be? Because not only would I be getting the weight of the carbon dioxide, which does have weight, you guys know even if it's a gas, it still has weight. But I'm also getting the weight of the latex balloon. So you guys, what should I do first, right? Before blowing into it, what should I do? Wouldn't I weigh the balloon? Let's say it's 1 gram, right? When you guys agree? So I weigh the empty balloon. Then I could blow into it. Then what would I do? Then I put on the scale. Let's say it says 12 grams. Then what do? Don't I just subtract out the weight of the balloon, which was 1 gram. So it was 12 grams, subtract out 1 gram, isn't it 11 grams? So now I have 11 grams. So maybe I need the weight, but let's say I want to know how much, number-wise, how much carbon dioxide molecules are in there, right? So I don't want the weight, but I might want how many moles of carbon dioxide are in there. Because remember, moles is a number. Okay? So we would just do the same. We would do the reverse. So let's say I want to know the moles. You guys remember with unit analysis, you do the endpoint first. I want to get how many moles of carbon dioxide. So we're just kind of making up a problem. And what do I know? What's the information I have? When I weighed that out, then I have 11 grams of carbon dioxide. So you guys, it's called unit analysis because we're analyzing units. So you look, what are we going from? We're going from grams to moles. Once again, what's the link between the gram weight and the mole number? You guys remember, it's the molar mass. So what do? I proceed to look up the molar mass of carbon dioxide. So I look, carbon right here weighs 12, oxygen weighs 16, and these are very close. Even when I go to the tens place, it's actually 12.0 and 16.0, so remember the tens place. So what do? I add 2 oxygen atoms, 16 and 16, because there's 2, it's 32, plus the carbon weighs 12, that's a total, if I add those together, it's 44. Remember we did that before. And how do I write it? It's 44 grams per mole. Once again, what does that mean? 1 mole of carbon dioxide would weigh 44 grams. But I don't have 44 grams, I only have 11 grams. So when you guys, even if you guys could predict, what are we predicting? Am I gonna have more or less than a mole of carbon dioxide? Wouldn't you guys agree? Wouldn't it have to be less? Because if I had 44 grams of carbon dioxide, it would be equivalent to 1 mole. I only have 11 grams, I have less, so wouldn't I would expect the number less here. So, once again, this is my link. So I just have one set of parentheses. Now notice, look, I'm starting with grams. So if I want grams to cancel out, grams on top, Which one of those do I put on the bottom? You guessed it. We put the 44 grams on the bottom. That's equivalent to 1 mole. So what we did is just use the molar mass and put it in there. Look, gram on top, gram on bottom cancels. And then look, what's the unit I have left is moles. Good indication I'm doing it right. Have this number on top, this number on bottom. So what do? You take this number, you divide it by that number. Some of you guys are good with math. You guys can reduce that down. 11 over 44, doesn't that reduce to 1/4? Right, isn't that 1/4? And what's the decimal equivalent of 1/4? You guys should know 1/4 is 0.25. That's a quarter, right? So, how much, assuming, so how much carbon dioxide do I have in this 11 gram sample of carbon dioxide? I have 1/4 of a mole of carbon dioxide molecule. All right. So, hopefully you guys were able to follow that. You guys work on the fun sheet that's associated with this, and we will see you next time. Bye, guys.